This is E1 and this is E3 bar transpose. Excuse me. I think I said it, but I didn't write it. All right, let me think through this. This is m by n times a n by m. What does that give me? Oh, it gives me an m by m. It makes sense that. So this here, this is really kind of this is a little bit sneaky, but here it is, Kronecker delta. So I usually do this stuff for square matrices, so it doesn't pop out at me as much, but this is technically E bar, E bar ik. So this is the m by m matrix unit. And so the product of an m by n matrix unit and an n by m matrix unit is the corresponding m by m matrix unit, like so. Now when we put n equals to m, and this is all square, it becomes much nicer. We can just have, so like for square, which I think is what I usually have the good sense to stick with, which is like pretty much all of our applications are square anyways. Why am I belaboring this? We have the following formula, right? Eij times E KL transpose apparently is equal to Kronecker delta JL EIK. Now, you might notice that, by the way, so that's an identity we can save for future use. But notice that EKL transpose is actually ELK, right? Because if it's got a 1 in the, that's where it's 0, if we transpose it, it puts the 1 on the other pair. And so the equation above we could also save as this Eij ELK equals to Kronecker delta JL EIK, which is how I usually remember this identity for like future use. Basically, when you multiply a product of square matrix units, you have to have that the matching, like the indices which are adjacent, they have to match up. Oh man, I just went over the hour. Son of a gun. I was going to try to stop right before the hour, and I have missed my spot. Anyways, you see how the JL have to match up for it to be non-zero, and then the I and K just kind of ride along. That's an easy pattern to kind of remember. And it's nice for... Okay, so all of this said, what does this mean for the matrix? So the matrix units are an obvious basis for the set of matrices, right? And so with all of this said, if we're... so you notice, like, if we look at Eij EKL in the m by n matrix units, well, that's the trace of what? It's the trace of what? Eij EKL transpose, which we just worked out, is the trace of Kronecker delta JL EIK. Which is what? It's 0 if J is not equal to L, right? And it's 1 if J is equal to L. And what? It's more than that. So J has to be equal to L to get that non-zero. And then in order for the trace of a matrix unit to be non-zero, the 1 has to be on the diagonal where we're summing, which is to say that I has to equal K. All right? So in other words, so you gotta understand how to adapt the statement of orthonormality when we're working with a double index. See, we're not enumerating the vectors in the space by a single index. We're enumerating the vectors in our n by n by a double index because it's convenient, because of course it has the meaning of rows and columns. And so in order for these two to match up, they have to have matching double indices, which is to say I has to match K and J has to match L. That's exactly what we need for the matrix units to be orthonormal, because they have the inner product of themselves with itself is 1 and 0. Right. And we can go through the same song and dance. Like if we want to let complex m by n space, right? If we look at that, it has, first of all, it has Eij, where I and j range from, as appropriate, over 1 to m and 1 to n. It has that as a complex orthonormal basis, because this calculation is unaltered when we dress it up with the conjugates, right? But you could also prove for over C, and you could also give it, well, there's 2 different ways you could go, right? You could do this, and then like that. And depending on how you order the matrix units, if you had like, your matrix was Z equal to X plus IY, where X and Y are real matrices, then if this is your gamma basis, then you'd have something like phi gamma of Z would be, like your coordinate vector for X and your coordinate vector for Y. Now, popular strategies for the ordering of the matrix basis are to order it so that when you chop the matrix up into pieces, you go like column by column by column by column. If you look at matrix theory books, they're usually built on like a columnification of the matrix, where they just have this thing they call vec, which takes the matrix and like strings it out, column 1, column 2, column 3, like that. But that's not in my notes, but I've seen it. And like, if you want to see that kind of thing, you should look in the book by Gullub. He has all of the like slicker matrix theory we'd ever teach people in linear algebra. All right. So that brings us to, let's see, let me just take a quick look ahead. We've got to talk about subspaces. We've got to talk about how to build an orthonormal basis. And I think that is pretty much it. Projections, perhaps. Orthogonal complement. So yeah, that's where we're going. And then you can talk about approximations with respect to projections, which leads you to the method of least squares. Those I want to project. Like, I don't ever want to write those out in here. They're ugly. And then, of course, the natural, like, this leads naturally to the discussion of, like, the Fourier expansion. And that's, And then I have a discussion of transformations which preserve the geometry. Those are orthogonal transformations, but I'm going to stop here for just a minute. I traditionally try to take a break in the middle here. I try to take it before the hour so I don't end up having 3 videos, but that didn't happen today. So.